Okay, our next speaker is Michael Turner. Michael is Rauner Distinguished Service Professor and Director of the Kavli Institute for Cosmological Physics at the University of Chicago. He helped establish the interdisciplinary field that combines together cosmology and elementary particle physics to understand the origin and evolution of the universe. Today he will tell us about the state of that field and some of the big questions we're facing. Please join me in welcoming Michael.
Thank you. It's really a special privilege to be here today. I learned physics at Caltech and how to think about physics at Caltech from Richard Feynman and his colleagues. And my introduction to Caltech was this auditorium. So I was a high school student in Los Angeles, and my high school physics teacher brought me to the Monday night lectures. I think they're called the Watson lectures now. No permission slips, no seat belts. I came here and I heard about things that I had never heard about before, and I knew this is the place I wanted to be. And so Beckman Auditorium holds a very special place for me. So let's see, I think I said this. I was an undergraduate here. Here are the years, 67 to 71. We learned physics from the Feynman lectures. Feynman was a very big influence on the campus, as would be shown by the yearbook here. So this was one of the yearbooks when I was here, so the Big T lectures on Caltech. And these are some pictures from the yearbook. Let's see, who's that? Oh, that's me. And here's Richard Feynman from that year. And this is Robbie Vogt, one of the other physics professors here who really influenced me. And the reason I show this picture of Robbie is that Robbie arranged for a tutorial between me and Feynman once a week for a quarter. And it was one of the greatest adventures of my life, and I learned a lot. And so the theme of my lecture here is kind of a little bit of payback, because cosmology was not, as you'll see, was not an area that Feynman was that interested in. So this is cosmology for Dr. Feynman. This is my telling him about where we are and seeking his help. It's always important to tell people what you're about to do is hard. So this is challenging because he wrote not one paper on cosmology. The closest were his lectures on gravitation. He was interested in fundamental issues that were ripe to solve, and ripe to solve means he wanted data. And that was not cosmology at his time. So cosmology was the province of astronomers, and it was not ripe for solving. There was not very much data. However, he once attended a colloquium I gave at Caltech on cosmology and asked me a question I'm still trying to answer. His partons, which I think we heard a little bit about last night, really was one of the first steps in pushing cosmology to be closer to fundamental physics. And so I'll talk about that. And what we've heard in countless talks is he was always ready to look at something, and if he looked at it, he was going to look at it in a new way, and so we could use his help in that regard. So let me start out slowly on the universe. So here are the basics. 100 billion galaxies in the universe, lit up with the light each of about 100 billion stars, carried away from each other by expanding space from a Big Bang beginning 14 billion years ago. All of this got started in Pasadena when Feynman was a teen in New York. So that was interesting for me to think about. I had never really thought about it that way. And Hubble, this is the sky. I don't know if you could see this from Far Rockaway. Maybe it's far enough from New York City that you could. But a big puzzle when Feynman was young was these fuzzy little nebulae. So that's the Andromeda one. That's the one you can see with the naked eye. What are they? And Hubble solved that riddle with the 100-inch telescope on Mount Wilson and showed that they were galaxies like our own. They were island universes. And so he enlarged the universe by a factor of 100 billion. We'll come back to that number a couple of times. And so here's the kind of picture we have of the universe today. with the space telescope named after Hubble. This is 1/10,000,000th of the sky, and I'm not going to show you this slide long enough to count, but there are about 10,000 galaxies there. And if you multiply those two numbers together in the right way, you get 100 billion. Of course, Hubble was also famous a few years later for discovering the expansion of the universe and the Big Bang. So he used that same telescope to find that those galaxies are moving away from us in a pattern that we call the Hubble flow. The ones that are farther away are moving faster. And if you look at that picture and extrapolate backwards, you find out that 14 billion years ago, they were all in the same place in a Big Bang. And here's a picture. I think this is a picture of Einstein at Caltech. And with some help, because when you're at the frontiers, things are really confusing. Einstein had help on this. The Big Bang is not an explosion of galaxies into space, but it's an explosion of space with galaxies being carried along. So when I was an undergraduate here, the big questions in cosmology were summarized by Hubble's student, Alan Sandage, who worked down the block from here. And he said, it's all about two numbers, H0 and Q0. I'll tell you what those are. Many people probably don't know what they are. And we're going to solve it with this 200-inch telescope the mirror was polished here. It's now called the Hale telescope at Mount Palomar. And so this is from a famous article that he wrote in Physics Today. Cosmology is just those two numbers. And so this is the size of the universe. I'm going to illustrate these two numbers. So it's expanding. And the issue is how fast is it expanding? Because if we know that, we can figure out how long ago was the Big Bang. And so that's H0, the expansion rate, the slope of this line. And it must be slowing down due to gravity. And so that's the droopiness of this line. How much is it slowing down? And so that Q0 quantifies that, and that tells you the destiny. And cosmology really was the province of astronomers, and there weren't that many of them working on it, maybe, I don't know, 30. However, change was in the air at about that time. A mysterious microwave signal was discovered by Penzias and Wilson in 1964. Radiation left over from the Big Bang, we call it the microwave echo of the Big Bang. And the import of this, for which they were given the Nobel Prize in 1978, we saw some stamps last night, so here's another stamp, was that the Big Bang was hot. And that starts to change the way you think about the universe in a fundamental way. And so you heat something up, you reduce it to its basics. That's starting to sound a little more interesting to Feynman. And so the universe is hot and simple. It's expanding and cooling. And I'm going to skip the quarks here for a second, but it does start with quark soup. Neutrons and protons. When the universe was seconds old, it was a nuclear reactor. And then it got cool enough for atoms to form. And when the atoms formed, the universe became transparent to light. And so this is the microwave background that Lisa was talking about, and we'll talk about some more. So we're starting to change the way we think about the universe. At about the same time, Feynman was thinking about what are neutrons and protons made of? Are there seeds inside? And there were some experiments going on at Stanford at the Linear Accelerator Center. And Feynman was starting to interpret those experiments with his partons. And so parton was his name for a stand-in that we now realize is the quarks. And so here he is giving a seminar at SLAC, writing some equations down about these constituents of the neutron and the proton that would make life a lot simpler and more interesting for cosmologists. And David Gross this morning talked about the standard model of particle physics, where this was all put together. The partons are actually the quarks that Murray Gell-Mann and others talked about. And here's the standard model. And so in the beginning, the universe was just a soup of elementary particles. And it was a lot simpler than it had any right to be for cosmologists to study. Okay, so in the 1980s, the standard model of particle physics allowed one to make big speculations that David talked about this morning about the unification of the forces, and that these ideas might even be relevant to cosmology. And so the cosmologists started exploring the bold ideas in particle physics. We heard about grand unification and supersymmetry and superstrings, and we supported ourselves with t-shirts. So here we have Cosmology Takes Guts. That's grand unified theories. Let's see, here's another t-shirt that helped pay salaries of postdocs. In short, this was a really, really great, some people call this the go-go junk bond days of early universe cosmology. It was a very exciting time to be alive. And I just want to pause here, and somewhere around 1980 or the mid-1980s, the conversation and the vocabulary about cosmology were changed. It was no longer Q naught and H naught. It was a different vocabulary. A big idea changed the conversation, and that big idea was the deep connections between quarks and the cosmos, this early quark phase and the universe that we see today. And the connection is very deep. It's not just that the universe began as quark soup. It's things happened in the quark soup that shaped and determined the way the universe would be today. So that's the big idea. And so, I showed you Q naught and H naught. And so this is today's vocabulary, much of which you saw in earlier talks today. Dark matter, I'll talk about inflation, dark energy, baryogenesis I won't be able to talk about, but Lisa talked a lot about where the dark matter came from. What about the atoms? So we have a theory of where the atoms came from, but it's a little more complicated and I won't get to it. We heard about WIMPs. So this is the new vocabulary. So the language of cosmology was changed. And it also brought in some outsiders. That's the wonderful thing about astronomy, is they welcome outsiders. I think Lisa gave you a flavor of it. At first, they don't like them, and they say, we don't need you. And then they became full members of the community, and oh yeah, we embraced you from the very beginning. You're really an astronomer. Kind of reminds you of immigration in the United States. So dark matter, that's the first piece. I don't need to say very much about dark matter. So the evidence for dark matter, Lisa mentioned the flat rotation curve, stars moving around the centers of galaxies much faster than they should be if they were held only by the gravity of the stars. And this is Vera Rubin, whose careful work demonstrated this in the 1970s. And the idea here is dark matter is a new elementary particle left over from the quark soup. And I think Lisa gave you a really great flavor of, okay, so that's the paintbrush version of it, but could we have a few more details? And the few more details we're struggling with right now. Inflation. So let me talk about inflation. So inflation is probably the most important idea since Gamov's idea of the Big Bang. The most important idea in cosmology since Gamov's idea of the Big Bang. And it involves an early burst of tremendous expansion, and I'll tell you what it's caused by in a second. And so why would we be interested in that? Well, that burst of expansion could explain the fact that when we look across the sky, and I'll show you some images across the sky, we live in a very smooth universe, smoother than it ought to be. The echo of the Big Bang, the heat of the Big Bang. Where did that heat come from? That's another big puzzle. And then there was a problem called the monopole problem that's no longer a problem that John Preskill worked on, and it also would explain why we're not overrun with monopoles. And it made some predictions about the universe. And what causes it? Well, our best understanding, which best does not mean correct, is that it has something to do with a field like the field that gives rise to the Higgs boson. So when Higgs boson was discovered, we were very excited because at least there's one scalar field in nature, and we describe all of inflation in terms of another scalar field. Let me talk about the most amazing thing that inflation does, which shows this deep connection between the very small and the very big. So inflation is a tremendous stretching of things. So Lisa mentioned that we had a lumpy universe at one time, small variations, I'll show you a picture of it, in the density of matter, and gravity got a hold of those, amplified them, and turned them into the galaxies and all the structure we see today. So where did that initial lumpiness come from? And inflation explains that in an amazing way. So it says, guess what? The lumpiness came from quantum fluctuations. So they have to be there. And you might say, well, yeah, I don't really buy that because, you know, they're on scales I can't even see, and you're talking about scales that I can't even imagine. How does that work? So these fluctuations on very small scales get stretched due to inflation to astronomical scales, and then there's a few details I haven't put in here. And so galaxies were seeded by quantum fluctuations. So that gives you a sense of the connections between the very small and the very big. The details of inflation were worked out at a workshop that Stephen Hawking held in Cambridge, England, and Caltech and Feynman's influence was on this workshop. Well, of course, Stephen Hawking was a frequent visitor to Caltech. Paul Steinhardt is one of the fathers of inflation. He was an undergraduate here. I don't know who that is. There's John Preskill. And this is Jim Bardeen, who's one of the few graduate students who did their PhD work under Richard Feynman. Okay, the third element that comes into the current cosmological paradigm is called dark energy. And this burst on the scene in 1998 with the discovery that the universe is not slowing down, but it's actually speeding up. And it's doing that because repulsive gravity is a feature of Einstein's theory. And I don't mean that studying his theory is repulsive, but that some stuff, rather than having attractive gravity, which that's kind of the defining principle of gravity, some stuff can have repulsive gravity. And this is very, very weird stuff, and we call it dark energy. And if you're puzzled, you've caught up with us. Okay. And our best example, of course, in Southern California, having Zen in your talk is good. So this is the Zen part of the talk. The best example of this is the energy of nothing. And of course, nothing isn't nothing according to quantum mechanics. It's filled with particles living on borrowed time and borrowed energy. And I'm sure you're going to trust me on this. It's easy to show that if quantum nothingness has energy, it has repulsive gravity. You'll probably trust me on that one. And theorists are very, very proud because when we figure out how repulsive the gravity of the quantum vacuum is, we get more or less the right answer. Well, to within 55 orders of magnitude. And, well, actually, it's not even that good. But so this is, I'm going to bring Feynman in on this. I'm going to remind Feynman that he knows this, but I'm going to remind him anyway to show him that I know that he knows it. So we heard about his tricks to get rid of infinities. And this is an infinity that his tricks didn't work on. So this is a really hard one. Okay, so we call this model that we have, sometimes we call it the concordance cosmology, sometimes we call it lambda CDM, because this quantum vacuum energy is mathematically equivalent to Einstein's cosmological constant, lambda, and lambda is shorter than quantum vacuum energy. So let me just tell you, let me tell Dr. Feynman how great this model is. So a jiffy after the beginning, the definition of a jiffy is down there, There was this tremendous burst of expansion, that's the inflation. It smoothed out space-time, created hot quark soup, and turned subatomic quantum fluctuations into the seeds for galaxies. Until the universe was 10 to the minus 5 seconds old, we had quark soup, and during that time, ordinary matter arose and dark matter arose. So you're starting to see that earliest moments of the universe are really, really important. From 10 to the minus 5 seconds to 300 seconds, this is when the neutrons and protons formed, and then some of them came together to make nuclei, and we actually have these elements left over from the Big Bang, and that's one of the big pieces of evidence. From 100,000 years to 5 billion years, the gravity of dark matter, that's what Lisa was talking about, builds cosmic structures from these quantum seeds. And from 5 billion years on, the dark energy takes over and the universe is speeding up. So that's our story. Here it is. Here's this very early quark soup phase that really didn't come into being until about the time of Feynman's death, where so many interesting things were going on here. Origin of dark matter and ordinary matter, and inflation. And, I'll show this next slide quickly. So gravity is building structure with the dark matter, and this is what Lisa was talking about, is we have lumpy dark matter, and so this theory predicts that you make small things first, like galaxies, and they have the visible part of the galaxy embedded in a much larger halo, and then clusters form, and then the universe starts speeding up, and the formation of structure ends. Giant computer simulations. This is very predictive. It says galaxies, most galaxies should be forming around redshifts of 2 to 5. If you don't know what redshift is, you'll see it in the next slide. So I'll bring in another Feynman quote. I mean, it doesn't matter how beautiful your theory is. This is a pretty beautiful theory. It doesn't matter how smart you are. Well, I don't know how smart I am. If it doesn't agree with experiment, it's wrong. And so what's wonderful about this story is that it's backed up with a wealth of experimental data. So I'll just show you a little bit of that. Oh, I've been talking about theory because Feynman was a theorist and because I'm a theorist, but we had some help from some powerful instruments. I believe those are the two Keck telescopes. And there's some really good telescopes in Chile too. And there's some really nice telescopes at the South Pole. Maybe we'll come back to those later, and we have telescopes in space. So powerful instruments help this story as well. So this is one of my favorite astrophysics slides, and it's from the Old Testament, so you have to read it from right to left. So here's redshift. So the cold dark matter, this dark matter theory said that most of the galaxies should be built right around here, and that's what you see. Here's time if you're interested in regular time. And what's shown here is the star formation rate. Galaxies are made out of stars. And so this is the kind of data that we have that tests this theory. Okay, let me come to the microwave background because this is a Rosetta Stone. This is really important. It allows us to see so I've blown up the last bit of my complete history of the universe. We look out into space, we look back in time, and the microwave background allows us to see the universe before stars, before galaxies, when it was really simple, and when theorists can understand it. And so the COBE satellite gave us our first good glimpse of it, and its resolution was not so good, not because it was a NASA failure, but because it was, that was the first try. WMAP had better resolution, and the best map we have from space is from the Planck satellite. So here is what the universe looked like when it was 380,000 years old. And for those of you trying to decide whether or not you want to go into cosmology, if you stare at this and your heart goes pitter-patter, you want to be a cosmologist. If you look at it and say, that looks like noise, well, actually it is Gaussian random noise. except for Stephen Hawking's initials there, SH. So if we do a magical mathematical trick to this called the spherical harmonic transform and plot the temperature difference between different points on the sky, look what jumps out. So we have these acoustic peaks and a curve that I hand drew through here. No, I didn't hand draw it through here. This is what the cold dark matter theory predicts. So that's pretty good. To Alan Sandage. The Hubble constant is 70. I'm sorry about that. I know you had your heart set on 40. And equally sorry that Q naught is negative. So Alan defined that with a minus sign so that if the universe was slowing down, it would come out positive. And so we have a 14 billion year old accelerating universe. And he thought Q naught would solve the destiny, but until we understand the dark energy, we don't know the destiny. I had to say, I already said this once, that the biggest things in the universe. So back to Feynman. So I've told him this story, and he would probably say, remind me, the first principle is that you must not fool yourself, and you are the easiest person to fool. And from firsthand experience, I know that's true. So let's talk a little bit about the chinks here. So here's this beautiful description of the universe, connecting the very big to the very small. And it's built upon these strong pillars. I wish I had an animation where the pillars start to shake, and of dark matter. Let's see, Lisa explained very clearly that we don't know what it is. Dark energy, I think I explained very clearly that we don't know what it is. And trust me, we don't know what inflation is yet either. And so 3 shaky pillars. And I think Feynman would say, okay, that's one way to look at it is from David's talk, the optimistic talk, this is new physics, or maybe it's stand-ins, maybe they're proxies, or I hate to use the word epicycles, but maybe they're just describing in the poor language we have today something much richer. So the big questions, what is the dark matter particle, or is that even the right question? What is the nature of dark energy or cosmic destiny, and why does nothing weigh so little? A question that we tried to ignore. When did inflation take place, and what about the multiverse? I'm going to show you one thing about the multiverse. How did ordinary matter originate? I didn't talk much about that. What happened before the Big Bang? So that's a great question. And I already said, are the 3 pillars just stand-ins? So I have to talk just ever so briefly about the multiverse. So in inflation, it's one of those things, it's the mouse and the cookie. If inflation took place once, it probably took place a lot of times. And whenever a physicist says a lot of times, they really mean infinity. And so here's the cosmic river of time. Here is the inflation that led to us. So everything I just told you is this, but there were a lot of other ones. And so the universe is a lot bigger than we thought. And so this is the multiverse. And the pieces are disconnected, so they can't communicate with one another. They might look very differently. The multiverse makes, Hubble's discovery that the universe is 100 billion times bigger than we thought, makes him look like a piker. It might even solve the problem of what the dark energy is and why nothing weighs so little is the multiverse. You have a landscape, the cosmic landscape of string theory that indeed in most places the vacuum energy is incredibly big, but in one of the 10 to the 500 universes out there, it's small enough. I'm going to borrow a phrase of someone in the audience. That seems like a very extravagant explanation for one fact. And I'll bring Feynman back in. The multiverse dilemma in my mind is this could be the most important idea since Copernicus, but if it's not testable, is it science? And so that gives me a headache. And so here's the Feynman quote I'll bring in. I would rather have questions that can't be answered than answers that can't be questioned. And I'm not saying the multiverse is an answer that can't be questioned, but I haven't seen a good way to question it so far. And I guess I have 1 minute left, or? Yeah, okay, so I see 10 minutes left. Well, let me just skip to the, well, I wanted to talk about testing inflation because I can bring Caltech in again. So inflation also predicts gravity waves, and they leave a polarization signature on the microwave background. It's called the curl or the B mode. It's a really critical test. And this experiment that I showed you earlier, the BICEP experiment, and the South Pole Telescope, that's the Chicago experiment, detected these B modes. Look at, that's what they detected. That's the swirl. That's amazing. Unfortunately, the first thing you learn about astronomy is dust is the bane of astronomers. And so, you know, is it inflationary B modes or not? And so far, we know some of it is dust. But I like to think positively there's room for something else, and gravity waves. And so this is one of those, the chase continues. This is one of these big things. So let me just finish. I hope that Dr. Feynman would be pleased with this story, especially that it's not over, especially that it is ripe for progress because there's data, and now because it involves fundamental physics. And the last thing I want to say, I added this morning because I realized Feynman is one of the few scientists, this is one of the quotes I haven't seen anyone put up, he was not afraid to say, I don't know. And I think I heard in every lecture somebody saying, and Feynman said, I don't know. And that is so important in science. And I don't know, but certainly his spirit was, and let's find out. I don't know, and let's find out. And so that's the cosmology adventure we're on. Thank you.
Hey, are there any questions? Right here?
Hi, thank you for the very inspiring lecture. I saw a figure that I didn't hear a full explanation of. I was wondering if you could explain the moose diagram.
The moose diagram. Well, Lisa explained that. Oh, and we can't see it anymore. So the moose diagram, oh boy, I get headaches in cosmology because I'm getting old. Maybe I'm just getting headaches because I'm getting old. But if we go back to the WIMP, and I've got a trademark on that Lisa violated. If we go back to the WIMP, we thought dark matter was really simple. We thought it was one extra particle, and that moose diagram, if you're a theorist, even if you say you have one answer, you really give three. And so one was the WIMP, or the neutralino, the lightest supersymmetric particle. Another answer was the axion, which comes out of QCD. And we thought life was really simple, that we were just missing one piece of the puzzle. It wasn't going to open the world to a whole new dark sector, and it wasn't going to make life more complicated. We were very close to the end. And that might actually be the case, but when I hear Lisa give a talk, I go, boy, I don't think I want to bet on we're close to the end. I think there might be more twists and turns. And so the moose diagram is sort of a relic of early simplified thinking.
Thank you.
Another question here?
So in the previous talk, there was a list of 7 or 8 concrete experimental sort of reasons why dark matter should be there. They seem to be pretty clear because dark matter can go through each other itself when things collide, etc. I take it inflation is sort of the reason dark energy should be there, but is there a sort of similar list of experimental evidence for dark energy?
Yeah, so the number one, so right now we don't know if dark energy and inflation are related. They're both accelerated expansion, but we don't know if they're related. In fact, I don't think there's any really good theory where they're related. So let's do dark energy. So the evidence for dark energy, the primary evidence is the universe is speeding up. And that evidence came in 1998, and the evidence was a little bit shaky. And the evidence has gotten incredibly stronger. And all kinds of, Lisa's list, we could make the same list for dark energy where there's ancillary evidence, the microwave background, clusters of galaxies tell us about the expansion of the universe. So the evidence is really, really good that the universe is speeding up, but we don't know what's causing it. And likewise for inflation. Probably my poster child for inflation was the curve with the acoustic peaks. So for both of them, we have really good, the universe is speeding up, but we don't know why.
On the topic of big questions, would you rather fight one Feynman-sized duck or 100 duck-sized Feynmans?
Uh-oh, you're going to have to repeat that again.
On the topic of big questions, would you rather fight one Feynman-sized duck or 100 duck-sized Feynmans, and why?
Oh boy, that's a dilemma. I think I'll take C. You had a C, right?
All right, another question over here.
You talked about the river of time kind of expanding into many multiverses, which
yes,
presumably with different initial conditions and parameters. Are there any thoughts on like why it suddenly triggers an expansion into inflation into a universe and kind of what the nature of that is?
Yeah, so the thoughts there are really due to Alex Valenkin and Andre Linde, that the same, here's the dilemma about the multiverse. So we like those quantum fluctuations that seeded galaxies. We love them. And we see evidence for them in the microwave background. And what Valenkin and Linde and others have shown is that those same quantum fluctuations seed other universes. And so that's the strongest argument for the existence of the multiverse, which is if you want those quantum fluctuations for galaxies, you got to take the other ones as well. Now, it turns out that Hawking's last paper just came out, and it was about the multiverse. And the wonderful thing about Stephen is he was in the fray until the very end. And his paper hoped to give, I don't think he liked the multiverse that much, hoped to give the multiverse a big haircut and made it a lot smaller. But the multiverse still gives me a headache. Does it give you a headache? Yes. Good, good. Then you're really smart.
I think we have a question over here.
It's two parts. I was in the supermarket and I picked up a prestigious-looking magazine which I'd never seen before, American Scientist, May June issue, as opposed to New Scientist, which I've seen all the time. And in it there was an article by an American-born cosmologist or physicist who is at an English or Dutch-based university, which states that the latest compilation of all survey material says there's 2 trillion galaxies, not 100 billion. That's question one. And the more interesting question is, in your diagram of the river of time spawning an innumerable number of universes.
So you know that's a Monet. That's abstract art. You're not supposed to interpret it literally, but continue with your question.
I'm sorry, I thought it was Kandinsky. I love Wassily. Anyway, what is, if we're going to have something as simple as the river of time, what is the origin of the river of time? What came before it, and what are its characteristics?
So let me answer the second one first by not answering it, and then I'll answer the first one. So that river of time is one of the answers to what happened before the Big Bang. And when we ask nature really, really hard questions, we say, is it A or B? Is it A or B? I know it's got to be A or B. It's D, right? It's C. And so when we ask what happened before the Big Bang, one of the interesting things about the multiverse is there was no beginning. There were an infinity of beginnings, and that should send you back to your desk to think new thoughts. So that takes you out of that there was, I'm not saying I understand it, but one of the nice, anyway, that's one of the nice features of that. The article that you read is fascinating. I'm teaching undergraduates, and I had them count the 10,000 galaxies in the Hubble Deep Field. And then I asked them on a pop quiz, how many are there? And so one of my students, and boy, you Chicago students are really smart. I don't know if Caltech, or I'm staring at your president here. No, Caltech students are brighter. And so the student said, I know I counted 100 billion galaxies in the Hubble Deep Field, but I Googled it on the internet, and it's 2 trillion. So I thought, oh, geez. So I went and Googled on the internet and found that article. And it's a very interesting article because those, if I understand it correctly, and we probably have some real astronomers in the audience, those 2 trillion galaxies have not been seen. But in this paper it was European astronomers from Holland. Where's our, from Holland. There, Robert. And said that, if you look at the Hubble Deep Fields, one of the amazing things in it are the train wrecks, that you're seeing the assembly of galaxies. So as an extrapolation back, that if you look at the 100 or 200 billion that are here today, the pieces that came together, there must have been 2 trillion pieces, is the way I read that article. But they didn't really see them. And so I don't think that counts. I think that the correct answer on my pop quiz is still 100 billion.
So if the river of time if it has no origin because that question has no meaning because it's infinite, why is there only one color in the Monet? How many other colors should be used?
Well, I'll let you know, artists never explain their work, so.
Yesterday, one of the speakers mentioned that there was that some people postulated that there was only one electron, and they use that to explain something.
That's wonderful.
And
I think it's even true.
And then and then they also, another one said that we really don't understand time. So
that's also true.
My question is, if there's only one electron, if that happens to be true, and we don't understand time,
how can we understand the universe?
Is it possible that there is only one photon in our universe? And in other words, if you are standing here and say you have a black hole in the middle and you have a star on the other side, that photon goes around the black hole, hits the star or galaxy on the other end, comes back, and then goes back, and then comes around, so we actually see 2 distant galaxies. But the time sequence that we have from our perspective is it's the same time, and that could maybe explain something that's going on there. And as far as dark matter, is it possible that there is another photon of a different frequency that we cannot detect simply because we don't have the physical ability to detect that photon, and that could have some explanation.
This is a complicated question. I encourage you to speak to Michael now that the session is over. We're a little bit over time, so please come on up and finish your question in person. So it's time to go to lunch. I want to remind everyone to take their belongings with them. So please don't leave anything in the auditorium. And there are lunch opportunities listed on the program. So we'll see you back at 2 p.m. Thanks.